Um, First of all, I would like to thank you for inviting me here. It's an honor to speak to you. And it's also interesting for me to speak to you about what made me write this book. Because when I set out to do that, you know, my field is living stars, not the dead stars. The living ones are actually much more fantastic than the dead ones, I think. Maybe you have similar comments on your profession. But anyhow, what made me write it was, first of all, that I thought that the general picture we give about the progress of science, not the least when giving out Nobel Prizes, is perturbed by the romantic 19th century era of the big heroes. While if you really start exploring, for instance, the development of the history of black holes, you may think of a few names, and I present, I think, 500 names or so. It's really a massive undertaking. And very, very many people are involved, not the least technical people. So that's the first point. But the other more interesting point, enigmatic point for me, was that when I started reading closer about the recent developments during the last 20 years of this field, in particular in theory, I find that my colleagues, you know, who are rather kind of straightforward and want to have a very clear logical reasoning and guided by equations if possible, they meet very remarkable problems. Problems that they try to solve, of course. And these solutions have a character which I'm fascinated by, but sometimes this character is, I would say, totally absurd. So when square-headed people like me meet very difficult problems, what do they do? And that is something I hope to illustrate a little bit in this talk. I was late for this lecture because geography here was changed since I was here last time. I can blame that. Time is a difficult issue, not the least when you come close to black holes. I'll show you now what would happen. First of all, I should say that this is a simulation. The way a black hole would look if you look at it, say it's at the distance of the sun. It has a mass of several at the distance of the moon, it has the mass of several suns. And then you would see it like this against the sky background, the stellar background. And you can see how the light from the background stars is bent in these peculiar bows called Einstein rings around it because of the curvature of space-time which the black hole exerts. I will bring you into a black hole in a simulation like this. So we are sitting roughly at that distance and we go towards the black hole. No, sorry. Here we are again. This is always a difficulty. Yeah. So you see the black hole and the bending of the stars behind, of the direction towards the stars, and we come closer and closer and the black hole opens up and we are reaching the horizon soon. And the whole world is collected above us, and below us is the black hole. And soon we will be at the horizon. The horizon is the region, the area which defines inside that light cannot come out. And there we are. And now you are welcome to plunge into it. What happens at this moment is a very interesting thing, namely that, as you know, in general relativity, space and time is woven together. So what is space for a person may be time for another one, vice versa, depending on how you move relative to each other, or what force fields you sit in. Here, the space-time curvature is so great that actually time and space interchanges character. So time, You know, time has this property of progressing, and you can't stop it, okay? From now on, when you cross the horizon, space cannot be escaped. Your orbit into the center of the black hole is totally bound. No way out. Just as time goes, now space goes. So it's a rather difficult situation for you. And when you come there, in particular if a black hole is rather light, like say 30 solar masses or 20 solar masses or so, which seems to be rather characteristic, maybe 10 solar masses. If so, the gravity in your feet, if you go with feet first, I would do that anyhow. If you do that, the gravity in your feet will be greater than the gravity in your head, and so you will be, as people say, spaghettified. So, from a medical point of view, I suppose, this is a difficult situation. Anyhow, I'll start a short history back, because there was a priest in the 18th century in a parish outside Manchester who speculated about a number of things. He was a good scientist too. He is actually regarded to be the inventor of seismology, because he was fascinated and worried about the great earthquake and tsunami outside Lisboa, which killed some 50,000 people. And being a priest, that was of course a problem. Why did the good Lord do it? But also, how did the good Lord do it? And so he invented the idea that there could have been an earthquake out in the sea, which led to this settling of sea bottom and the big tsunami. And he calculated where this epicenter would be. He was interested in astronomy. He built a telescope, he observed double stars, which was a new thing to do. And he also speculated, starting from Newton's theory of gravity, which was 100 years old, and well established, of course. And he said that there is a speed which you need to have, say, in a rocket, if you want to come outside the Earth gravity field. And that's called the velocity of escape, flykthastigheten in Swedish. And you can calculate that speed. It's 11 kilometers per second. So that's what a space probe needs in order to get out of the field of gravity of the Earth. Anyhow, if you now think of compacting a star, having big enough a mass within small enough a radius, and the radius will be on the order of 10 kilometers, and the mass on the order of solar. So it's a very compact state of matter. If you do this, then nothing can get out of it. Light cannot get out. That's the point. And he knew that speed of light had a finite velocity of 300,000 kilometers per hour. And so he could calculate this radius. And he described this calculation and sent it to a friend who was a member of the Royal Society, the Academy. And this is then actually the so-called dark stars, the very invention of the whole idea that you can perhaps have matter which is so compact that you can't see it, because nothing can come out, not even light. The velocity of escape is at least equal to 300,000 kilometers per second, the speed of light. Okay. He also told how we could discover them, these so-called dark stars, and that would be to look for a binary star. I said he was interested in double stars, binary stars. You look for a binary star where one of the components is revolving around an object which you can't see. And by measuring the speed of this revolution of the visible component, you can then calculate the mass of the unseen object. So he pointed at this possibility of discovering it, and that's actually a basic method to discover black holes today. So this was a pioneer, and then of course, as always in science, I would say, there was another fellow who got the honor of this. He published a great number of books, the famous de Laplace, a great number of books, and including one very, very well spread one, which was Napoleon, read. And anyhow, there were several editions, I think more than 10 editions of this book, and there he presented this idea and actually calculated this velocity of escape. So here, as did John Mitchell, the real pioneer. Here you see that the velocity of escape, let's see if I can get this, is equal to square root of Newton's gravity constant times the mass of the object divided by radius. So a small radius gives a high velocity of escape, and if this velocity comes up to c, then you get the critical radius and you get the dark star. You could try to remember this expression because it'll come back. And so this was an interesting topic, and the Romantic era adopted it, of course. Dark stars out there, and you can read poems about the dark stars, but rather soon they were totally killed. And they were killed by the discovery by not the least Thomas Young and Fresnel and others, the discovery that light is waves, not particles. And so the whole reasoning here is wrong. You can't think of light as bullets shot out by a cannon or rockets sent away. Light can go out whatever gravity field you have in classical theory. So there were no more dark stars in science for a century. And then came, of course, Einstein. And as you know, I hope, the general relativity has a much more sound and much more understandable description of gravity than the old Newtonian theory. The old Newtonian theory is manifestedly mystic, and it was criticized very much by his contemporaries. I mean, the very idea that if I would release this now, it would fall down to the earth. Because of what? Because of a mystic hand which comes up from earth and pulls it down, a hand which you cannot see at all. What's that? So Descartes and others during Newton's time regarded this to be just mystic. It's metaphysics. The idea worked, and you could calculate wonderful things with it if you scaled it the right way. But it's not a very physical understanding at all. It's no understanding at all. Action at a distance. What's that? So Einstein's idea was considerably simpler. His idea was, sorry, yes, if you have that. Thank you. Einstein's idea was space-time is an object. It's a plastic object. And mass has the property of curving space-time. So the space and time around the sun, say, is curved. You can think deformed by the mass in the sun. And so the Earth goes straight forward. But space-time is curved, and so it gets an orbit around it. And this is the common way of displaying this for children in science centers. So you collapse the three-dimensional space, at least, to a two-dimensional surface, say a rubber sheet. And you put your Earth, which is a mass, say of lead, you put that on the sheet, and you get this kind of curvature of the plane. And if you then throw a small marble, stenkula, in here, you will see it's encircling the mass in the center. Not because the mass has some kind of very mystic attraction onto your marble, but because, thank you very much, because the mass curves its space-time around it. This is 100 years ago. So if you haven't really thought of this, please bring it in here and tell your small kids about it. This is not modern physics. This is a very classical theory. which works very well. In practice, it's difficult to handle because you need rather advanced mathematics. You need tensor calculus and differential geometry. And that was the main problem. But conceptually, this is much simpler. I mean, think of the old idea. There is space, say, a theater scene, like the floor here, that space, okay? And then in the background, you have a clock which goes independently of space. And then the actors, that's a matter, plays their performance, their theater play. And this is the kind of division of nature which you are used to because you were taught this. And it works very well in your living room. But if you have a strong gravity field, you see that this is not the way it is at all. First of all, already if you move at high speeds without any gravity, you will discover that space and time is interwoven, so that your space is linked to the clock going and affects each other in the sense that if you move rapidly, the clock goes at another speed as you recall it. Okay? That's proven in the lab, no doubt about that. But then, in the general relativity, space and time is deformable, curved by mass. So, instead of having this scene and this clock and these actors, you have a big object, a huge object, transparent object, but deformable object. And matter curves it. So all matter, all actors affect space and time. And space and time affect the way actors move. So you have a much more kind of beautiful dual situation. Space, time, and matter. And space, time is deformed by matter. And matter is governing the motion of space-time is governing the motion of matter. I think it's wonderful. Mathematics is actually also nice, but as I said, rather difficult. I thought, since you invited me here, I should have these kids. And actually it's from a literacy calendar, but it serves its purpose here. Because I want to illustrate a fundamental principle behind general relativity. Einstein didn't build it from mathematics. Actually, he had great difficulties with his math. He wasn't at all very brilliant a mathematician. But he built it from his idea to be very consequential, very systematic, logical, and beautiful. So he took this picture, and he built it from what he called the equivalence principle. And what's that? It's basically this. If you sit in an elevator, and somebody cuts a cable up on the 10th floor, you will have a travel down. And then if you, during this travel, want to enjoy yourself, because before the crash, you can make some physical experiments. And then the whole idea was that whatever you do, if you send light rays, if you have nuclear reactions, if you have some ball rolling in, whatever, play football, whatever you do in this elevator, the same behavior of matter will be seen in the free-falling elevator as you would see out in free space. So you are weightless, as people say it, in the elevator in exactly the same way. And if you don't have a window out of the elevator so you can see there's a difference, you can't say whether you are falling due to your cable being broken or whether you are out in space. That's not an obvious idea at all. Of course it's not. But it's beautiful if it were true. And Einstein then set out to build his theory as if it were true. And it turned out then that he had to introduce curved space-time in order to get it working. He adopted that. There was a full theory of curved space-times in any dimensions developed by a number of mathematicians in the end of the 19th century and early 20th century. So there was no new mathematics needed, but the mathematics was rather difficult. But I want to illustrate then how you can reach a fundamental truth about this space-time thing and gravity by using this idea of Einstein. And that is, you assume these kids here to stand in a rope ladder. You don't need to have books in the steps, it may be just pins like this. They stand there. There's one fellow standing rather low, and then there's another fellow upstairs standing higher up. Okay, they stand in the gravity field of the Earth, and they stay there. And what will they feel? They will feel the gravity from the Earth. And so this fellow who stays in the bottom, he will feel a somewhat stronger gravity than the one upstairs, because he's closer to the center of the Earth. And gravity is depending on 1/r². That is the square of the distance from the center of mass. So he feels a somewhat stronger gravity. Okay. In his feet, then, there'll be a push. So if you start thinking of old-fashioned forces, although gravity in this description is not a force, it's a curvature of space-time. But anyhow, if you think of it in terms of forces, there is a gravity force going down from the green-brown man there, and there's a counter force going up from the ladder onto his feet. So if there wasn't any gravity, he would be accelerated upwards by this force in his feet. A force exerted by the ladder. That's okay, is it? Okay, you seem to be a little bit skeptical. I assure you, this is elementary physics. Anyhow, the fellow upstairs, he must feel a somewhat smaller gravity. It's a very, very tiny difference, but it is somewhat smaller because he's at a greater distance from the center of the Earth. So the force accelerating or trying, that would accelerate him upwards if the gravity weren't there, that force will be somewhat weaker. Okay? This is a minor difference, but it is there. Okay. So we can live with that, I hope. But then comes the equivalence principle. What does that say? That says, let's bring the whole experiment out in free space. And they should have exactly the same experiences. So, this fellow here, he should now feel a force in his feet of the same strength as that force. He should find a pressure here. And this fellow should find a somewhat smaller pressure there. Where does it come from? Well, the only way of explaining this is, of course, to accelerate the whole thing. So you pull your rope ladder with high speed in this way. So the idea, the equivalence principle of Einstein is, okay, this is totally equivalent to an accelerated elevator. I mean, here the elevator is not falling down. Here it's standing still. And that corresponds then to acceleration out in free space. And by having this acceleration of the ladder, this fellow will feel the pressure in the force in the feet, and so will that. And then comes the clue. This fellow should feel a somewhat stronger acceleration than this one. Okay. How do you do that? Are you going to pull this ladder and accelerate it? That's conceivable. But then that force, that pressure on his feet would be the same as this pressure on his feet. But they are different. How do you make it? What you say is that when you measure the acceleration of this guy, you measure acceleration in meters per second. That is velocity change per second. Meters per second, meter per sekund kvadrat. You measure that. You have a different second, a different measure of time than here. So if time goes slower here than here, this force locally will be felt stronger than this. And still the full ladder will not be pulled aside or falling together. The ladder will keep its shape if you require that time goes slower there than there. And that's exactly the point. So if you go into a gravity field, time will go slower the closer you are to the mass. So if you travel into a very, very massive object, time will go very slow, as seen from the outside. So when we traveled into the black hole in the very beginning here, we who travel in, we will do it in, say, a few minutes and cross this horizon. While if we sit and watch, say me, if I do the travel and you watch me, you will see my clock go slower and slower and slower. In the end, I won't move. And you tell your grandchildren to tell their grandchildren to tell their grandchildren, etc., to watch the fellow on the border of the hole. And they cannot never see any movement on my part. Maybe in 40,000 years they can celebrate because my watch has moved 1 second. But it's even worse. If we keep telling our grandchildren, generation after generation, in infinite times, literally speaking, infinite times. Let's assume that humans can, for some mystic reason, survive on Earth for infinite times. They will never see me crossing, while I will cross in a few minutes. I've had that experience that the universe is collected above me, the black hole is under me, and then I cross. And I can see the evolution of the universe through these minutes. I can see the sun expanding in 7 billion years. I can see the galaxies dispersing in 100 billion years, etc., etc. Literally speaking, I leave your time. So it's not so easy to believe in this. And so people didn't do it. And one of the people who didn't believe in this was Alva Gullstrand, who got the Nobel Prize in medicine physiology in 1911. And he was a specialist in astigmatism. And in order to work out a theory, he had to acquaint himself with mathematics and not the least with non-Euclidean geometry. And so he was the right fellow to understand what Einstein had done. And also he had a reputation which was high enough to place him in the Nobel Committee of Physics at the Royal Academy of Sciences. And in that committee he fought systematically against Einstein as a Nobel Prize winner. And the reason why he did this is really interesting, because people say lots of bad things about this fellow. I read the original papers, I've read papers he published, because he published papers on the solution of Einstein's theory of relativity equations, the field equations, for the spherical symmetric case, that is for a black hole. And the interesting thing is, and this was in 1921, that he found another solution than this fellow did. I'll come back to that, but I'll first introduce Karl Schwarzschild, an astronomer, a very, very gifted person, and he then served as a volunteer in the First World War as an artillery officer on both the West Front and later on the East Front. And actually he got this pemphigus, which I think you know what it is. It's an autoimmune disease, skin disease, I think, which killed him. And towards the end of his life, just a few months before he died, he got a copy of Einstein's papers. He saw the field equations and he succeeded in solving them, which Einstein hadn't done. So he solved them for the simplest case, a spherical symmetric mass. First for the point mass and then for a spherical symmetric mass. And he found this infinite curvature of space-time if the radius was greater than this, which is exactly the equation we had before. So if the radius was greater than this, he found that there is an infinite curvature. I don't think he liked that, and Einstein absolutely didn't like it. People didn't believe it. Nor did Alvar Gullstrand, because Alvar Gullstrand, 4 years later, when there were lots of people who had nominated Einstein for the prize because it had been confirmed by observation, the theory had been confirmed by observations of a solar eclipse. Anyhow, Gullstrand said, no, it can't be right, because I found a solution here. And that's different from the solution that this fellow had found. And so Gullstrand argued, this is a worthless theory, at least at the moment, because you get different solutions depending on how you do the mathematics. That was a valid point. What he didn't understand was that in general relativity, geometry is rather complex, and so it's not easy to see if you can get one expression by transforming to another coordinate system. So Gullstrand had found a correct solution, as he had, and you could actually transform the solution from one coordinate system to another one, and in that way show that they were equivalent. That wasn't proven until 10 years later. But the Gullstrand, the non-believer, the critic, his contribution to the theory of general relativity, and in particular to the theory of black holes, is probably the most important contribution by any Swede to general relativity. It's used a lot today. It's a much more useful way of solving these equations than the method, the coordinates used by Schwarzschild. So, he's worth some credit, I think. Anyhow, then was this observation of the solar eclipse in 1919, where one could see stars out. This is a negative picture, so this will be dark. That's the lunar disk and the corona of the sun. And here you see some black dots in the middle of these bars. And those moved a little bit because of the bending of light in the curved space-time. And they were moved to the places which Einstein had proposed, roughly. And so Arthur Eddington was the man who did this, and this made the theory very famous, and Einstein very famous. I think I discussed this in the book. There's lots of interesting cultural history here. You know, we had this Second World War, and this fellow was British. Einstein was a pacifist, but still he was a German. And here one could see that, okay, humanity is progressing. The two sides contribute to a fantastic discovery. Einstein got very, very popular immediately, and as you know, he was a very charming person. Then came a number of other persons, like Subrahmanyam Chandrasekhar, who later on got the Nobel Prize for his work on the mass limit of white dwarfs. Essentially, he came to the conclusion that the normally accepted ending stage for a star, which people believed every star would end up as a white dwarf star, but it couldn't have a greater mass than roughly 1.4 solar masses. And there are much more heavy stars, and what did they end up as then? And it's very interesting episode in this history to see that Eddington didn't like at all Chandrasekhar's point. And this quote is taken from one of his objections. I'll read it to you so you understand some of the feeling. The star, any star he means, must go on radiating and contract until it, I suppose, has shrunk to a radius of a few kilometers, when gravity is strong enough to hold the radiation back and the star finally rests in peace. That's a black hole. I think there must be natural laws which stop it from behaving so absurdly. They were considered to be totally absurd. And no wonder. Why? Because there are infinities. And physicists don't like infinities. We try to avoid them. And of course, everyone thinks of infinity in all directions. You move and there's no border and you can't set it. So universe probably, you say, may be infinite or should be infinite. But we don't talk about that here. We talk about infinities in among us. So if there were a black hole here, it was be like a well, infinitely deep. So if I would drop anything into it, I would never hear it reaching the bottom. So you can walk around these infinities. And still, the very idea that they are there was an ugly one. There are very few people who believed in them. Here are at least one. So this fellow is Fritz Zwicky, and we're talking now about the 1930s. He is a remarkable figure. Actually, he was the discoverer of the dark matter, which is 5 times more than all visible matter we see, and which fills the universe and probably consists of small particles that move through us, billions or at least millions of them every second. They essentially have gravity, so you see the effects of them in clusters of galaxies, and that's exactly what Zwicky did. He found that clusters of galaxies were behaving as if there were much more matter than he could see. He was also the inventor of the neutron stars, and he was also one of the pioneers in supernova research. He also had this idea, he had lots of ideas. One of them was that everyone should help in cleaning the toilets in the department, which was discussed. And he was also collecting lots of library books to send to developing countries and countries destroyed by war after the Second World War. He had a number of patents on rockets. He worked for NASA, and one of his more remarkable ideas was that if you shoot a proton ray, a ray of protons, a beam of protons, shoot that onto the sun in the right way, you can get the sun to respond by sending out lots of charged particles. And so the whole solar system could move, driven by this solar rocket, and reach the neighboring Alpha Centauri star, which is 4 light years away, within 10,000 years. So he proposed this kind of excursion for humanity. And there are many other such ideas. So when he said, I think that these black holes exist, and he called them Hades-Objekte. He was Swiss, so his native tongue was German. When he said, I think they exist, I don't think that was a strong argument for anybody. He was regarded to be a very fanciful man. This fellow, you know him, he's the father of Manhattan Project, the scientific leader of the American atomic bomb in the Second World War. He was a splendid physicist and a very inspiring fellow, and a very odd personality too. By the way, he took a stand against development of nuclear weapons, a pursuit of it into hydrogen bombs in the 1940s, early 50s. And for that, he was regarded to be non-American. Anyhow, this fellow, he set 2 students to calculate whether a star could shrink into a black hole and what would happen. How would it work physically? And I think if there were Nobel Prizes to be given for the discovery or for the theory of black holes, and if he was still alive, he would be a very good candidate. But there is a kind of distressing fact, and that is that in the early 50s, a physicist, well-known physicist, Hong-Yi Chu, he asked him about his early pioneering papers on black holes from 1939. And in answering the questions, he said, Oppenheimer, I never believed in that, you see. I've never believed in that. It's too absurd for me. No, but these students wanted to have something which was about glorious, and so I said they can try to do this. So maybe he wouldn't deserve a Nobel Prize, but I wouldn't like to give it to Zwicky anyhow. Here is a real hero. A mathematician from New Zealand, who actually in the early 60s realized, and I think people did that, but he found the solution of it, that black holes should be rotating. A rotating black hole is natural because any star rotates. And when it collapses into a black hole, if it's massive enough, it most probably does so, because it can't get rid of its mass, but nor can it get rid of its rotation, the angular momentum, as we say. So it spins up, and it spins up to a very high rate because it falls from several solar radii into something which is just 10 kilometers or 20 kilometers across. So it spins up. And then he Roy Kerr found the solution of Einstein's equations for rotating black holes, and he found that space-time is swept by the black holes. And if you come close enough to a rotating black hole, you can't avoid being swept with the black hole. You are forced to circle it. And that's called the ergosphere, and actually this ergosphere, which you cross outside here, you can go in, you can go out, but you get a very great kick. And if you read science fiction novels, this is a very popular way of getting energy for these interstellar civilizations. You know, they go to a black hole, they put up a frame here, a steel frame or something, and then it starts rotating, and they have a dynamo which is driven by this and can get up enormous amounts of energy. Actually, this is one of the most enormous energy sources in the universe. I'll come to that. If you go on traveling here, you reach this outer horizon, which is similar to the horizon I talked about for the Schwarzschild black hole. So what I've been talking earlier on is this infinite curvature occurring in the middle of the black hole, and you come inside the horizon, and time and space shifts. But anyhow, here again, time and space shifts. So here you have to pursue your travel, but then you get into a second horizon. And there they switch again. So you fall into the black hole, you reach the horizon, you can't resist following a certain orbit in through the second horizon, but there you can steer if you have enough of rockets. And so you can avoid the very singularity. And lo and behold, the singularity now is not a point infinity, it's a ring. So keep away from the ring, and you can pass. And this happens also in science fiction novels, that people do that, they steer through, and they get out in what is called a wormhole. After, you know, in a board, a worm has gone in somewhere and it comes out somewhere else. So if you are successful in your travel, you can get to another place and another time in our universe, or possibly in another universe, if such universes exist. And this has been a very popular topic in science fiction. Okay? Now, the problem is that you have quantum mechanical effects. All these theories are based on classical understanding of matter, but you have very dense matter here, and this dense matter needs to be described by quantum mechanics. And so even space and time must be quantized, and so I would say it's probable that these wormholes are not accessible, that you will be destroyed long before by vacuum fluctuations and violent phenomena inside, but we don't know. The father of the wormholes was this John Archibald Wheeler, and he is famous because people think that he was the man who coined the term black holes, like in the obituary, which I found in New York Times. That's wrong, however. There were articles before that published by this lady, Anne Ewing, who was a science journalist and an ambulance pilot in the Second World War. She is quite an interesting figure, and she then used this first in print in 1964, the term. But the man who actually seems to have used this, according to what I found from interviewing people, was Robert Dicker, a very remarkable physicist who gave a talk, a seminar, or several seminars actually, where he talked about black holes in Princeton in the early 60s, and he then compared the black holes to the famous black hole in Calcutta. What's that? Well, that's this event where the Brits, or soldiers fighting for the British East Asian Company, they were captured by the local Nawab of Calcutta and put into a prison. And there were 150, according to the war propaganda at least, 150 of these Brits put into some room which was 5 by 4 and 3.5 meter high. And there was a small opening up here. And when the morning afterwards they opened the doors to it, 100 of them were dead, suffocated.
But what about the black hole in Malmö?
I'll come to that. I have a picture of it. Thank you. Anyhow, so this story was spread from 1756 by the war propaganda in particular, and the whole idea of the black hole was there in culture in many places, including here, including in Malmö. So, you know, there was Hotel Svea here, which was a fine hotel where you could have a nice stay. But then in the evening, if you wanted to have some more adventurous experiences, you went down to the Black Hole, as it was called, Gärdsgården, the house nearby. So black holes is not a term invented by astronomers at all. Then came these discoveries of very, very violent phenomena, like this galaxy, which is big as the full Milky Way system. It has thrown out two enormous bubbles of very, very energetic electrons and magnetic fields. These are among the biggest objects in the universe. It's several million light years across. Or these very compact objects, which were shining like several galaxies, but not bigger than the solar system. And there was this discovery of the X-ray sources, which were these kind of binary systems where you have one big star encircling a small object which you can't see, except for lots of X-ray radiation coming out from a neighborhood here, which is probably or certainly produced by matter, pulled by this heavy but invisible object, pulled, and where the atoms collide intensively and create this X-ray radiation. And then there was the discovery of the pulsars, very compact, rapidly rotating objects, spinning many, many turns per second and sending out very regular pulses. And one could identify these stars, these pulsars, with neutron stars, and they are not much bigger than a black hole. So if you have matter and compress it to a neutron star, you are rather close to getting a black hole. If you load more matter onto a neutron star, it will have to collapse. And then there were these three groups. It's interesting fact, one in the US one Russian, and one British. It's interesting that all these are very active during the Second World War in weapon construction. These two fathers of the hydrogen bombs in the Cold War, and Dennis Sciama, one of the pioneers in radars. And they had this habit of working in dense groups of young people, and they attracted, when they came out of the war or out of the Cold War, they found this area of general relativity to be not very densely populated. So they can, being medieval, or mean age, having ages of 40 or 45, they could start anew in a new area which was not very populated. They would have no chance in elementary particle physics, but when they came and saw this new field, they could do something, and collected youngsters among them, and they were very good at that. And Dennis Sciama in particular, who had these fellows and several others, very leading figures. And Hawking and Penrose showed this theorem, which was fundamental. That is, you can't really avoid singularities with a decent, physically decent method. There were no way out of them. If you at all want to keep general relativity, it leads to these singularities, to these infinities. There's more to say about that. One basic thing here is the contribution by Roger Penrose. He was a mathematician, and he introduced topology, advanced topology, you know, the mathematical theory of shapes, into the whole understanding, which helped a lot. Because after all, the basic point in relativity is there are no forces, there is geometry. You convert from the physical idea of forces to deformed space-time, to geometry. And then topology gets very important. And then we have this no-hair theorem, or théorème de Calviti. I like that because that means skallighet. And here idea is that whatever you throw into a black hole, you can't say afterwards what was thrown in. The only thing which remains as seen from the outside is mass, a possible electric charge, and the angular momentum. That's the rotation. I don't have time now to go into details, but this fellow whom we met earlier, he made in 1983 this clear statement that the most beautiful objects in the universe are the black holes. Mathematically, they are extremely beautiful. So you should remember that they are not only ugly. For many theorists, they are fantastic and beautiful. And then came the understanding of how these quasars and these radio galaxies are driven by their rotation. So the black hole in the center rotates. It has a disk around it, a disk of infalling matter, which is swept around by this ergosphere. And then there are magnetic fields in that disk. And these magnetic fields, they are knit together by this very spinning, and electrons are accelerated by these out to very great distances. This is the key element in the radio galaxies and quasars. And so these objects are driven by the spin. Rotation energy of black holes is a major energy source in the universe. And then came the discovery of the black hole in the center of the Milky Way. Here you have the ESO's European Southern Observatory, which we use a lot. Sweden is a founding member of this. These 4 8-meter telescopes that collaborate and collect light together. And by projecting a laser beam up to the upper troposphere, you get a small dot up there which you can use as an artificial star, and so you can get very sharp images using that artificial star to correct, by having adaptive optics, correct for all the turbulence in the Earth atmosphere. If you are interested in how one does that, I can tell you more then. Anyhow, this is a film made at ESO, where you see the innermost stars in our galaxy. You see it's only 10 light years across, and this is about 30 or 26,000 light years away from us. Anyhow, you can see what happens when time goes through roughly a decade. I'll show you a film. No, I won't. Try again. And now we zoom in, and you see how these innermost stars sweep around this cross in the middle, which is the center of the Milky Way. And they do that very, very swiftly. And by measuring that speed, you can measure the mass of the point here, and it's smaller than the solar system, and it has a mass of totally 4 million solar masses. And these are the two people who did this. Reinhard Genzel and his group from the ESO observatory, which I showed you, and Andrea Ghez from the Keck observatory on the American side, independently. And there are other black holes, like one which is thought to contain 6 billion solar masses. And all this is fine, and I think I have to end, but I will end then with a LIGO discovery. I have to say a few words before that, because what I wanted to tell but haven't time to do, but you can read about in the book, and which really took lots of my interest, is that you have a fundamental problem with the black holes. They aren't understood at all, and that is related to what happens when you cross the horizon. And the problem is the following. When you cross the horizon, we can't see you any longer. Okay? And you will not see us, because our universe has vanished. It has taken an infinite time measured in our universe for us to reach this stage, but you have crossed it after a few hours, say. Okay? Now you are inside, and no information can get out. But Stephen Hawking showed in a famous paper from 1974 that in the end the black holes will evaporate. And how do they evaporate? Due to quantum effects, and they are rather elementary. So I can teach my third-year students about this, and they understand it. Yes, black holes will evaporate due to quantum effects. And that'll be a kind of explosion, but it'll take enormous time before they do it, on the order of 10 raised to 70 years. So why bother about that? Well, we have bother, and people do bother. Why? Because when they evaporate, all information about you, me, who fell in, should come out. In the sense that the basic property of quantum mechanics says that all information of the wave functions that have gone in there has to come out. If you say that, no, it's destroyed in there, then we got a fundamental problem with quantum mechanics. It's really fundamental. This is called a break of the Unitarian principle, which we don't want at all. So we'll destroy an essential feature of quantum mechanics. We'll have to reform it drastically if information can't come out. So I say, okay, I fell in, I probably squeezed to death, of course, and all this, but in the end, after 10 to 70 years, information will leak out. Okay? But general relativity with the equivalence principle, which I told you about, this elevator falling and all that, that one tells you absolutely yes, no information can come out except for a meek Planck radiation. No more. So we have the two theories, quantum mechanics, general relativity, the two grand theories of last century, in total confrontation. And confrontation will happen in 10 to 70 years in practice. But still, you can read about one paper a week on this. And lots of these most bright people, Stephen Hawking, Penrose, John Ellis, many others, have been essentially discussing this. And they discussed this last year here in Stockholm also. There are meetings on the information paradox. And it isn't resolved. And the problem is that one doesn't want to give up one of these fantastic theories that work so well. And in that situation, and I just introduce a feature of the solution because it's of a solution which is rather common now. It's called black hole complementarity. And that's inspired by Niels Bohr's old way of solving the problem of how to understand quantum mechanics by saying that a wave function can manifest itself as a particle or as a wave, and it may, in a way, be either of those. And so you have a kind of double bookkeeping, which people criticize, but here it's worse. It says the following: black hole complementarity means that when you cross the horizon, if I do it, I will fall through. I won't notice anything, except for this with the universe above me and all this, you know. But I can survive several minutes in through the black hole in my time frame, while you will see me burning in a fireball on the surface. And that burning will give you all information about me. So this information never comes into the black hole. The problem was the information that was lost in the black hole. When did it come out? But here the answer is, it comes out. When you cross your horizon, all this information comes out, and there's a nice fire for you to see, and I'm lost from your point of view. While I don't notice that at all. And how can they do this? I mean, why do I allow, or why do we allow our colleagues to come with this kind of double bookkeeping? And the answer they give is the following: elegant or very questionable. Namely, I, who fall in, can never tell you guys that I'm alive, because I am inside the horizon. And you guys can never tell me that we have seen you burn to death, because you have vanished from my time. So, what's the problem? Do you get this? You can read it in the book, and if you can contribute something, it's nice. The community divides itself into three sectors. One is, I think quantum mechanics is totally wrong here. It doesn't work for gravity fields. And the other says, I know that general relativity is wrong, because that's a classical theory. It works with continua while world is quantized, and you have to take that into consideration. So they blame each other. And there are arguments for but also against both these two ideas. The third one is to say, no, there's a compromise. It's called black hole complementarity. But both are right. But quantum mechanics is right for you guys, so see me being destroyed and get your information conserved. While general relativity is right for me. I fall through the horizon, and the equivalence principle is valid for me. And that's enough. Okay. I hope your admiration for physicists has increased, not decreased, as a result of my presentation here. Anyhow, with this kind of doubtful situation where even Stephen Hawking argued, you know, he has spent his life on these black holes. He argued, maybe they don't exist because of the information paradox and the evaporation after 10 to 70 years. He was willing to give up due to this thought experiment of 10 to 70 years ahead. Okay? Came this discovery. So LIGO, as you saw in the news on February 11, had already on September 14, 2015, got the discovery. Here are the two arms, interferometer arms. So light is sent back and forth here, laser light, 4 kilometers long, and you measure the position of the mirrors to an accuracy better than an atomic nucleus. It's fantastic. I mean, I know these people. I followed this from the very beginning because I was very familiar with one of the fellows. I said, no, I could never do this. Okay, but they did it. And so they built one of these in Louisiana and one up in Washington on the west coast, the state of Washington. And the idea is to try to detect the shaking of space-time, which is a phenomenon which Einstein already could foresee. So if you move heavy masses close to each other, the whole space-time vibrates. It's called gravitational waves. It's in a bit the equivalence for gravity, equivalence to the electromagnetic waves for electromagnetism. Anyhow, these are very, very, very small. So we talk really about vibrations in a few seconds with a frequency of, say, 100 hertz or so, and which aren't bigger than, say, an atomic nucleus or less. And then the idea is to do it on 2 places at least, because then you can hopefully in that way see to that your signals are not due to earthquakes or thunderstorms or traffic for that matter. Okay. So the discovery of these 2 merging black holes, you see 3 different stages here. The first one, they are encircling each other, they lose energy, they fall together in the middle, and then you have a ringing in the end, and you have signals in the bottom. And here are the signals which they discovered then in this enormous amount of data. So you have the Hanford, that's the Washington detector, and you have the Livingston data, and they are very similar, as you see, and occur on the same time. A small shift because the wavefront comes in and hits Livingston first and then Hanford. You see, it takes about 1/10 of a second, the whole phenomenon. And you see here curves, the signal curves, which is the noisy ones, and the simulated, predicted curve, which is the full line. And from this you can deduce a number of properties of this system, where the 2 black holes had typically 30 solar masses and merged together at a distance. You can get an independent distance measure here, and the distance is 1.3 billion light years. And actually, by looking at this last phase, the ringing, you can actually also determine the rotation. You can see this curvametric in action. So I consider this to be a very, very good demonstration. The object is called gravitational wave 15, that's 2015, 0914, that's the date. Okay? So it's the GW 150914. It has proven, I think, that gravitational waves do exist. They are measured directly here for the first time. And also it proves that general relativity is valid also for strong gravity. Because earlier on, we had only confirmed it at rather weak gravity fields like that of the sun, with the bending of light, and etc. But here you find it very clearly valid for strong gravity. And it shows, I think, absolutely the best demonstration we have that black holes do exist. And also probably it proves the existence of the curvametric. So you have experienced an historical event. Congratulations. I'm sorry I've used time. I could say that time goes slowly for me, being closer to the black holes than you are, but maybe that's not a very strong argument here. Okay.